Thank you.
So today's last class, we begin with this chapter 6, deal with the 3D problem. And today we just do some examples or practice for in the Cartesian coordinates, since that will be included into this final exam. I think that is all we will go today and the last class. Okay, remember, we always deal with the separation, right? So that if we, okay, that is 3D problem in Cartesian. Okay. If it is separate, right? So if we can write down this partition separate correspond to each individual coordinates, then what we know, the Hamiltonian. Okay. This operator. The Hamiltonian operator can also separate, since the momentum is separate, right? So the Hamiltonian is the kinetic energy part plus potential. Kinetic energy is this in the Cartesian is Laplacian, which is separable. So then we can easily know that the x components, y components, and z components, they are separable. Then from here, so next we know the wave function can be a product of x components, the function of x component, y component, and z components. Then go to the Schrödinger equation, right? So that is we are going to solve. I use capital, okay.
Question.
Yes.
When we're doing separations like this, how do we know when to do separation additively and separation multiplicatively?
Okay, that is Hamiltonian. It is. And we will do one example. You can see the potential is additive, right? So Hamiltonian derivative is additive. But function itself will be product. Since function is always function of these three variables, and that's a product, it's not additive. That makes sense? Yeah. If you okay, suppose it's additive, when you substitute into this one, you will see there's a product of x, y, x, right? So that is not separable. You cannot separate them. I mean, the wave functions will always products of this each individual part. So when we deal with this here, then we substitute this one here, and this one here. So what we have three equations, right? Only x components. This is we already discussed last time. We reached to here, so today we are going to do examples. This we already did, right? Remember? So I think we separate here. Then by solving this, suppose we solving this Hamiltonian Schrödinger equation or eigenvalue problem, finally we found this is what we are going to do, right? Obtain the total energy of system. That energy, or eigenvalue, is simply the addition of these three. Each individual we have solved from each individual Hamiltonian Schrödinger equation. Then we can also simultaneously obtain the eigenstates. So each individual eigenstate and then the total eigenstate is here. So that is strategy. Now we are going to do some examples. First one, free particle. Okay, free particle, we know that potential x, y, z is 0, right? No any potential. So if 0 cannot write down into 0 plus 0 plus 0, which is this one's Vx, Vy, and Vz, right? Can I write this way? Because 0 is also 0 plus 0. So that means the Hamiltonian Okay, let's first write down here. Kinetic energy part, right? It's the operator of the kinetic plus potential. Then now we have this one is minus h bar square over 2m partial square partial x square plus partial y square plus square partial z square. That is this term, right? And plus, okay, vx plus vy plus vz. And each vx, vy all are 0. So we can write down the Hamiltonian or separable. Okay, each one we know that is the one dimension Hamiltonian, right? Plus 0, that's Vx, which is 0, right? And Hy is same thing. Y square is equal to 0 and z. So that is immediately know that is additive. Okay. Then we know, by this we know we are going to solve, let's say, we are going to first solve this one, x components. First one, right? Let's look this one. This one we know that is the chapter 4 very easily. I think you can use partial or direct, that's fine, but let me use partial here. Right, just so this one. And this one is kx, so kx is, remember, that is one dimension free particle in chapter 4, the first problem we solved. So we immediately use this result, and the result, let's give you a solution. So from here we got k, that means you can have the ex, x, 2m, h bar square k x square, right? Immediately got ex. Then the xx, remember that is we use this plane wave, right? So now let me just give you already normalized. That is or I mean, just go to your result from the chapter 1, the chapter 4, one dimension. So very easily we have this. And then similarly, because the other y and z, they are same. The only difference is replace the variable x by y, right? So similarly, we have. I need to write down again. Okay. So similarly, I just do this one. Ky is 2me. Okay, let me use this. I do not need to write the details, but here, so similarly, y hat y equal to ey y, and we know ky is defined 2mey or h bar, so that gives us energy associated with y, which is h bar square k y square and 2m, right? And the y is also plane wave, but with this wave factor or k is ky. Then this z part is also we have kz 2mez h bar. So that gives us ez is h bar square kz square m, and z is okay. So that's why we first play on the one dimension, so we can, when we extend to the 3 dimension, we can apply the result if we, separable, then we can apply the result for this 3D system. So now totally, this is each individual. Now we are going to go to here. The wave function, total wave function, and total energy, right? So the solution, final solution for the 3D, in 3D, 3 particle system. Now the wave function, let me first use energy. Energy, okay. Now I'm going to use a K, since it depends on the K, right? So now the is Ex, Ey plus Ez, right? And that is here. 2m h bar square kx square plus ky square plus kz square. If we define this is the k, so that is simply. So here we introduce the vector k, which is a kx, ky, and on the y direction, and kz. Direction. That is a vector, wave vector. And this vector now in 3D, right? So we have the components. In 1D is only forth and back. So now, if we have vector, energy you can see only depend on the magnitude, right? Does not depend on the direction or orientation. So that is the first one, the energy. Now, also the wave function. Since you see the wave function also depend on k, right? So I'm going to use the index k here, index k vector. Since here you see this, I didn't use vector because it's only depend on the magnitude, right? Here. That is x, y, and z, right? So each individual will have this one. So that is 1 over 2 pi, 3 over 2, right? It's the factor here. Then this exponential I kxx plus ky y plus kzz. And that is vector, inner product of vector between k and r, right? So I can use I k r. Now the k is vector in 3D. So you see here, because it depends on orientation, k. Therefore, the wave function depends on the orientation. I use k vector. But energy is only function of the magnitude of k. Okay. So here, you see the allowed k. There's no any restriction on this k value, right? It is continuous. So k vector is positive, negative, and also the r is also vector, right? So it's positive, negative. So that is give us all the continue. And all right. So this one continue. Continuous vector of energy. That is the same as we found in the 1D, right? Now we are going to have a brief discussion since we discuss details in 1D. So we are going to use that information go to the 3D. And we're already familiar with this, so I'm going to just give 2 points which different from 1D, right? What's different from 1D? 3D and 1D. First one. Let's look this one. Okay, so energy only depends on the magnitude, right? As I say here. So what that means? Okay, see here. Suppose this is x, y over z, right? So this is a k. Okay, I use x like this. Otherwise, you will confuse with this k. So this is a k vector. This k vector gives us the orientation ks, ky, kz, right? So now, if we have the magnitude k, that means all the k points in the sphere surface with a fixed magnitude. So you can have either any k right here. This is a k prime, k double prime. But they have same magnitude. But they have different wave function here because it's inner product this one, right? This one, if this direction different and the inner product is R is different, right? So what that means? Infinite K orientation. Oh yes, I did something orientation, right? On the surface, on the sphere, spherical surface of the K space, right? When I say K space, is in terms of K. So what that means, the degeneracy. How much degeneracy? Degeneracy means for the same energy value, we have how many states, right? Infinite, right? How about in 1D? Remember 1D? How much degeneracy? Just either further or front or back, right? Only 2 degeneracy. But when we go to 3D, it's infinite. That is different from 1D. They discuss the degeneracy of the system for given energy. Okay, I think that is the one different or properties. Now the second one, I think you. Okay, let me first. The stationary states. Stationary state of this free particle 3D, that means for given K, right? No. Okay, given K, there's a function, the particle in the space and a time t, right? With the same energy, that is a stationary state. If you do not remember, go back to chapter 3, we defined, right? So the spatial case, that, okay, I think to distinguish, I use a capital 5 here, right? Okay, let me just remove this capital here. So then this one is a spatial part, which is K, only function R. And remember, this is since Hamiltonian does not depend on time explicitly, we can separate Schrödinger equation time-dependent part and the time-independent part. This is a time-independent part, and we function product of time. This spatial part multiplied time. Remember, time is exponential, right? Minus I e k t or h bar. Yeah. That is for given energy, the wave function of the particle, evolution of wave function of particle is function time for giving energy k. But this one, as we know, the orientation of k is infinite, right? So that is have infinite states correspond to the limit. That is stationary states. And sometimes they can also write down this way. Instead of energy, we use omega. Omega k t. So here omega k is just energy ek over h bar defines. So that is this frequency of this plane wave in space. Okay, then this orthonormality of this one is this stationary states. Different k, but this different k is for the same energy. So that is this product, right? Now let's draw down here if you agree. So that is the integral of this k prime, this conjugate t and multiply itself k and this is the to the inner product, right? And you substitute this one, where to see it, right? This one, and with this product, this, so that is, we have this, we have this one, 1 over 2 pi, 3 over 2, and then multiply 2, so that is 3, right? Minus, okay, 3, right? Then that exponential, this one exponential I k r, this term, right? So, but here, this is a prime, so I'm going to use k prime, and this is minus, right? Take this. So here, let me see. Minus is this one, take minus. So this one became minus, here I have a minus. Let me take minus outside. But this minus became plus, right? But that's fine. I think let me just minus I minus I. Let's go this way. Okay. Here minus plus is that one, is this one, right? And minus this one. That is, of course, we have this term, this one. This omega t, right? So that we have I omega k. I use k prime t, right? Minus omega k t d q r. Okay. But we know since we use this one, right? We just consider the magnitude, same energy, but a different orientation. So this one is 1, right? Then we keep continuing, so we have this exponential now minus I k prime minus k. And this one, we know when k is a delta function, right? When k prime is not equal to k, it's be 0. If yes, singularity will go to infinite. So that is give us orthonormal. That the different wave function for different k, they are orthogonal. But only when k equal to same, so this be, but we know this is not normalized because it's go to infinite. That is our next question or next discussion. So that first gave us orthogonal behavior. Now this is number 2, stationary states, right? Number 3. Because we know, or you continue discuss this one too, right? So then one division, we already know this is when k equal to a k prime equal to k is not equal to 1. So that is not convert. Or the wave function or plane wave actually cannot be accepted as a physical wave function to describe this free particle as quantum states, right? Because either use the stationary or use this one. Is physically unacceptable due to this infinite, right? When this or not converts when we k prime equal to k. So remember, we have to take that the real or physically acceptable wave function this function is a superposition, right? Superposition of this term, right? So for all the k, or we call it wave packet. That we already discussed in one dimension, right? So we've got it now. The physically acceptable the wave function for the free particle in 3D is also now we are going to define this linear combination or superposition of all the k, so that is 2 pi 3 over 2. Now integral for all the k, I'm going to give a function. And with the states, with this okay, since okay, let's use this one, exponential I k r k in the parentheses r minus omega k t dk. Since we do the superposition is for k, right? For different k. Some also here, this integral is for k, and each individual k is a plane wave. Is this one, right? Is this one. So that be physically acceptable, and we already proved that it is finite. The inner product is finite, or square integral is finite. So the details I will not do, but this one I gave you this one. Remember we introduced this one is weighting factor in this case, and mathematically it's a Fourier transfer of this one, right? So that is very easy. You know this. We make it symmetric, so this the normalized constant the same, and integral okay. Here first. This is down here. This one is not this one. This one is the initial states of the system. The states of so that means if we have I'm going to initial state or states that give the function, maybe arbitrary function which is characterized, this be also real states, not not this one, right? This is one of the plane wave. And then this is just like coefficient. I project to this one. If you remember in the cat, that is the states project to this eigenstates or basis vector, and then they have a components. So that components for given k, we will have that, or you can say that is coefficient, something like that. Remember, if we have cat any states, you can linear combination of c, let's say ci psi I, you know, something like. Remember this? Sorry. Any states is, if let's use Tn, and this eigenstates. So any state we can linear combination express any states in terms of this either you use this base vector. In this case is eigenstates over the plane wave. Then the C, if you remember C, how to obtain C is the initial states. Let's just T now. Project to this one, right? And that coefficient. So this one seems like this. This is a coefficient that means you have all these bases. So this is a plane wave as a basis, and then this is your initial states. So that gives us how much the weight. That gives us this one, and then the real states is use this one, give a weight, and linear combination is this. Right here.
Are you saying that inside of the integrand it should be T0?
Yeah, I think it's be T0. And it's given your initial states, and then you have this coefficient like this. Then you know this coefficient given because this states are different, then this coefficient different. So you categorize this one as different. And here, this one is a Fourier transform of this, and we know this Fourier transform is nothing but you have to obtain this one if you know the initial states and you project to over this plane wave. So this integral is in real space. R, this one is phase space. Okay, and the remaining is because we know this wave, if the wave packet is the real quantum states to characterize the free particle. So we remember we have introduced two velocity. One is a group of the wave packet, group speed. So is the how much the change of the energy with respect to the momentum, or the energy is h bar omega, right? Okay. P is h bar k, right? So that is d omega k dk. That is group, and this give equal to the speed of basically or correspond to the classical speed of the particle, right? Of the free particle. And that equal to twice of phase. And let's use the phase. Phase speed. And the phase speed is in the wave. This is a kind of a particle behavior. This phase is the wave behavior, which is giving us the wave. We can define the speed of wave is the ratio of energy with this one. So that is ratio of this friction shear with the k. So that is if we use a plane wave, we can also cannot explain why the speed. This speed does not characterize the speed of the particle, because this is characterized with wave, and we know that it corresponds to each given plane wave. But if we characterize by the wave packet, the speed of this wave packet actually is equal to the speed of the particle. So that basically interpret this also successfully. This is we already discussed in the 1D, right? I just try to remind you. So this is the first example. Now we go to next one. In 1D we have an infinite square wave. So now how about 3D? Something like similar potential. So we are going to discuss this case and see how can we solve this. Box potential. So what is box potential? Is that if we have x in the 3D space, right? So this is from 0 to this is A, and this is B, this is C. Then it says that if the particle is filling into the box, no potential, or potential 0. Otherwise, infinite. So that means the particle restrict to the box, right? They call the box potential. How to represent the box potential in terms of mathematics? So V, that is 0 within the box, right? So within the box means this x, y, z has a limit within the x, within 0, this is 0, right? 0a, and then that is, and then the y speed with between 0 and b, and z speed between 0 and c. And then infinite else here. That is box potential. Okay, can we write our this potential can be separable? So now let's see this one. Because you see here, this means I can rewrite this one, if you agree, Vx, x. Now let me first write down, and I will give you what is each individual. Now the Vx is x direction, right? So x direction means along the x direction the particle only when the x between 0 and a is 0. Other infinite, right? So this potential is 0. Else. Yeah. This is 1D, infinite, right? This is like a 1D infinite square wheel. Remember? Similarly, y is also 0, but y from 0 to b, and else infinite elsewhere. Same thing, right? Same thing, and vz. So this is the first step. You need analysis, and then after you analyze, you got this conclusion that yes, it is separable. The remaining part is follow the same procedure. Right? So now, let's do this one. That's good. Okay. So we have H is separable too, because the kinetic energy part is separable. Therefore, if potential part is separable, then the Hamiltonian is separable. Then we have solved the 3-time independent Schrodinger equation. Oh, okay. And also the wave function is products of these 3 parts. Okay, so what we do is just solve the time independent Schrodinger equation for each individual one. Are they same? If you see the box, the widows is not same, so we need to solve each individual, not exact same, right? Since if the symmetric is low, then if symmetric high, we can apply the symmetric properties and to save our time. But this one is not symmetric, it's a cubic, right? Sorry, it is a rectangular. Okay, so the solution, since we already know this one, right? So now let's get to the solution. I just immediately go to the solution since we're familiar with this. Let's first the solution for x. X direction. If you remember, we have plus kx square x, but here kx is ex rho h. And okay, now what is x? Here, different from the free particle since we have a limit, right? Remember that? So we have a boundary condition, right? So x in general is this sinusoidal function plus e cosine x. So we are going to apply the boundary conditions at x equal to 0 and x equal to 8, right? We have 2 boundary conditions here. 0 here. Outside with 2, all are infinite, so that the wave functions be 0. If not, inside, so we have this. If you satisfy this boundary condition, you just substitute x equal to 0, thus be equal to 0. So x equal to 0, and also speed x equal to 8, right? So this is a condition. Right? Outside of this speed 0. So if you apply this to here, you will find this one speed no cosine, right? If x equal to 0, cosine is not 0. And this one is 0. So if you ask 0, then only the b is be 0. So finally, the x, okay, now I'm going to write down here. X, just to remind you how do you obtain this kx over x. then kx. Since we all, if we up here, then x equal to a is also equal to 0, so we have a kx is not continuous, not the arbitrary value, is be quantized or limited is by here, this required, okay. By this one we have the, okay, just kx equal to nx a over pi, and nx is from 1 to all the integer numbers. That is 1D. Infinite square wave we discussed by this boundary condition, right? So that is the then we have immediately got ex, right? Ex by this relation here, ex is h bar square k x square over 2m, right? So here now ex is 2m h bar square kx. Now kx is equal to this one, so I'm going to say we have a square and nx square pi square. So here index is, instead of use let's see, instead of use x, I'm going to say nx. It's a quantum number. So energy is quantized over discrete because boundary condition. And this kx give this number, quantum number nx, then the ex also quantized, right? Also this discrete. So we have this. Then finally, this if I substitute kx into here, so I have also x energy and function, right? X I'm also use index nx because that is also given in x. We will have a given one function that is a sine k is a over nx pi x. Then we are going to normalize. Since final functions, we normalize, if we normalize each individual part of a direction, then the total here should be normalized. If this normalized, this normalized, this also normalized, it will automatically normalize, right? So now let's normalize this one. Then you will get easier to get the 3D. So normalize. Normalization. We're going to have this from 0 to a, right? X, nx, x nx times dx be equal to 1, right? You say why not from minus infinite to infinite? Why? Because when x lower than x, 0 is 0, right? You don't need that part. And when x over a is also 0. So your integral from negative infinite to positive infinite equal to this. All right. So from here, okay, that's very simple. Substitute this into here. So I think you also already played this. A is square root of 2 over a. Now finally, the normalized. Now I'm going to rewrite this again. Normalized is this function. Nx pi x over a. Now we finish 1D for the x direction, and you do the same thing for others, for y and z. This is just to remind you when we play with in the 1D, infinite square wave, right? This is what we obtain. So similarly, we have a ey. Okay, I'm going to use ny, eny because same thing, right? I think I jumped a little bit. I think you agree with that. Because now the y is b, right? Be careful. So this one, this kx is nx over a pi, right? But y is different. So now let me give you here nx. So now I immediately give you the energy h bar square pi square. The only difference is nx becomes ny, right? 2m ny square. Ny also from 1, right? We discussed cannot be 0 because 0 is limited by the 0 energy, right? 0 energy at quantum mechanics has always followed the Heisenberg uncertainty principle. So always has a delta x and delta px. So that is why we this energy. And then the y also index ny, which is also normalized. Normalized, the procedure seems this factor is b, but here is b. Right, so then the sine ny pi y over b. Because this potential is not symmetric, it's not cubic, right? Then similarly, E and Z, h bar square pi square over 2m. Oh, I think I have this one, b square, right? It's a c square and z square. And z also from 1. And z and z normalized 2 over c sine and z pi z over c. Okay. Once we have each individual, finally we can have the total, the eigenfunction of this particle limited in the box potential and energy. So we can discuss the generation or behavior of this function. Right? So now, finally, we have the total energy E now is E and x plus E and y plus E and z. Now I have those, right? I take the same factor outside, so we have h bar square pi square over 2m inside n x square over a square, n y square over b square, and n z square over c square. So you see the index depend on this, so now we also write down E and x, E and y, E and z. Depend on 3 quantum numbers. Total energy. For given set of 3 quantum numbers, you have 1 energy. So you can change n, x, n, y, and z, and then you will change the energy, right? So that is energy, and the total wave function, x, y, z, and here is n, x, and x, y, and y, z, and z. And we have for each, the normalized is this one, right? A, right? A, B, C. Here, right? This one, 2, square root 2 over A, square root 2 over B, and square root 2 over C. If they multiply together, that's 2 to the q, so that is 8, and denominator is ABC. Then sine nx pi x over A, sine ny pi y over B, sine nz pi z over C. So again, this is also the index, so now I'm going to use index. It depends on this quantum number. It's not arbitrary. Now this is final, the eigenstates of this particle in 3D and eigenvalues, or energy and state function, right? So we obtain this. Oh, okay. I need to, sorry, this is my mistake. Yes, I need to here. That is for the case in this region box, right? If not, then this is be 0. And 0 is there. So that is now index. The result, this is 0, so that y we have this here, right? I already discussed. All right, now we are going to make a few discussion about some points we are going to discuss. Usually the discussion is the degeneracy, and what is the ground state, what is the first excited state, what is about the degeneracy of this system, because degeneracy depends on symmetry, right? So now let's see how the symmetry affect this degeneracy. The first one, Okay, let's look at the ground state. Ground state. Ground state is, now we look at the energy when energy lowest. Which one is lowest? Nx, Ny, Nz, which number? Nx, Ny, Nz, smaller number, the smaller is the lowest, right? So all start from 1. So that means if Nx, Ny, Nz all take 1, right? That's be smallest. And all the others be higher since here. Right, this is a positive value. So here, if this one, that means E ground, ask what is ground energy, so that is 1, 1, 1. Nx, Ny, Nz takes 1, 1, 1, so that is 1, 1, 1. And then you look here, so here that is h bar square pi square over 2m 1 over a square plus 1 over b square plus 1 over c square. And now let's look at ground state, this energy and this wave function, or the eigenfunction is this one, correspond to this index. So now we come to here, right? So that's be equal to 1, 1, 1. Also, I'm going to use 1, 1, 1, x, y, z. That's be here, right? So a, b, c, sine nx equal 1, so that's pi x over a, sine pi y over b, and sine pi z over c. Do we have more states? There's only one, right? So what is the degeneracy? No degeneracy, right? Just one state. No degeneracy. Okay, so or no, you say no degeneracy. Okay. Now, first, excited state. This is we need to analyze. The first excited state is that from here we take which value of nx, ny, nz such that this energy is just above this one and smaller than others. Which one?
Take any of the n's.
Increase by 1.
Equal to 1? Okay.
Equal to 2. And the other
All right.
one's equal.
Okay. So now let me first, okay, let's say x equal to 2, right? And other 1, 1. So this case is x bar square pi square over 2m. 2 is 4, right? I'm going to say 4 over a square and 1 over b square and 1 over c square. Now another one, 1, 2, 1. Y and y equal to 2, but the other equal to 1. That is 1 over a square, 4 over b square, 1 over c square, over z equal to 2, 1, 1, 2. So about these 3, which one is lower? We need more information.
Whichever one is the larger.
A, B, C, yeah. Which one is larger? Because denominator larger, then the number is smaller, right?
Right.
So the only difference here, then we are going to see we have a condition because they are not same, right? Definitely is not same since A, B, C not same. So we need to say we need additional condition or give us information. So if A larger than B larger than C, then which one? Then the first excited state, E first excited equal to which one? If A larger than B and C, so this one is smaller than this one, right? Smaller than this one. Because this is a hyperfactor 4, so that is the increased part compared with the ground state, right? Ground state, this is a ground state term. So that is 2, 1, 1, right? But if I change, for example, B larger than A larger than C, then this be 1, 2, 1. Right, so that is dependent. Okay. Then once we have this, you can see the states 2, 1, 1 is again we have constant psi. Now the nx 2, right? But the ny and z is still 1. Degeneracy? How many states? No degenerate, right? Again, because no any other states similar with this one have the same energy. So do the same thing. You can do the like a second. If I ask you to second excited state, I leave it for you. Think about if still use this condition. So which one? And the reason why no degeneracy because so the symmetry is lower, right? Along x, along y, along z are not the same. The symmetry is lower or low symmetry of the potential. Now we discuss number 3. If ABC the same, so that is cubic, right? That is a high symmetry, right? Since there's either along x, y, z they are same. If a symmetry increase or increase, let's see the degeneracy. So then the energy in x and y and z is here. A, B, C the same, so I take outside, right? Is if I use A, right? H bar squared pi squared and then nx squared plus ny squared plus nz squared. See the difference? Then the states nx, ny, and z. Okay. A cube. I didn't say that, but you will see this very clear. ABC is a volume, right? AQ is also volume of this cubic. It's a volume of the rectangle, so I just keep it. Then sine nx pi over a sine ny pi x y over a sine n pi z over a. Now, if we discuss in this case, how about this first ground states and steady states, you will see the difference. This difference is totally from the symmetry. So, how about the ground state? Again, we know that nx, ny, and z takes the smallest value, which is 1. So here, 1, 1, 1, okay. 1, 1, 1, which is h bar squared pi squared 2 m a squared 1 squared plus 1 squared plus 1 squared with a 3, right? So that is the ground state. Yes. Okay, this still. Let me take it down here. Sine pi x over a, sine pi y over a, sine pi sine pi z over a. Degeneracy. Still 1, right? No any more states because the index energy only when nx, ny, and z equal to 1, this lowers. When we change nx, ny, and z, they change energy, so that is another state. Let's say first excited states. Here, we don't need this condition since they are equal. So now you look here. Okay, I think I just look here. So because this is a constant, and this is a constant, either nx equal to 1 or 2 or ny equal to 1 or 2, they are same, right? So very easily, the energy is first excited is 2, 1, 1, 1, 2, 1, 1, 1, 2. They are same. That's equal to h bar square pi square over 2m a square. And one of these two square, another, there are 2, 1, another only 1, 2, right? So that is 6, right? 2m a square over 6 h bar square pi square. So the degeneracy we have 2, 1, 1 by 1, 2, 1 sine 1, 1, 2. They correspond to the same energy, right? First excited. This gave us the degeneracy. How many? 3. But here, it is no degeneracy. Reason because these are not symmetric. So you see, with the symmetry is with the degeneracy. And I will ask you, how about the second, right? You can also play this highest excited state. And degeneracy. Before I go to the harmonic, I think I will just extend the discussion more a little bit. Also normally. All the states, right? So that is depend on nx, ny, and z in the product of two states, nx prime, ny prime, and z prime. We know each in, okay, I delete, but this x, y, z, right? Each one we already have this degeneracy, so that is definitely when nx not equal to nx prime, it will equal to 0. This is one dimension, right? So that you know this one. I think that's very easy. The degeneracy here and also completeness. That sum of all the nx, ny, all the states together is equal to 1, one or unit operator. That is all the general behavior. Now, any states, right? If the system starts from not the one of the eigenstates, but any arbitrary states for any arbitrary states, how to write down? If I use any arbitrary states, any time of the system of the particle, we can always extend the linear combination in terms of the eigenstates, because eigenstates completeness and also form this basis set, Hilbert space, right? So in the Hilbert space, any vector in Hilbert space can be expressed in terms of the linear combination of all the project to this basis, right? So that is this coefficient depend on the states nx and y and z, and linear combination, right? And this is the eigenstates of nx and y and z, x, y, z. It's a spatial part, and the time-dependent part is energy exponential minus I, E, and actually, I don't need the separate. Just E n x plus E n y plus E. That is E. Just the E n x, n y, and z, t over h bar. E n x and y is a is here. It's here, right? That one. So then what's this nx and y and z summation for all these possible states? Then the coefficient, how to obtain the coefficient? If we know the initial states, we can project initial states to this eigenstates. So we have, and we give this in the Dirac notation, and then in the position representation is integral. X, T naught, oh, sorry, it's X naught. This is R. T naught, which is a 3 integral of sine nx and y and z, x, y, z. Is the initial states. X, y, z, dx, dy, dz. If asked this question, you need to find this coefficient C, N, X, and Y, and Z. Give you the initial states. Here, you have this, so you can give anything at any time resolution of the wave function. Then if ask expectation value, any operator expectation value, how to do? We have this definition, expectation value of these arbitrary states. Inner or sandwich of operator between these two, is between the states, right? And if the state is not normalized, you need to normalize this denominator. Right, that is definition of expectation value. Then what you need, just substitute this one into here, into that, so that became this states, and this we have two summation, nx prime, ny prime, and z prime, and nx, ny, and z, because each one has a summation here. This graph has a summation with a complex conjugate, and this one also. So c and x prime, y prime, and z prime, and c n x, n y, and z. Then the remaining part is the inner part or sandwich of between the eigenstates in x and y, z. There's a term here, right? Multiply exponential I minus I e n x prime y prime z prime minus e n x and y and z t prime. Then denominator. Denominator is simple. Y prime and z prime and x and y and z. C and x prime and x prime and y prime and z prime, C and x and y and z. And then delta and x prime, delta and y prime, delta and z prime. The reason here we use this one, because denominator is multiply itself, right? So that is inner product of this term, this one, and this one is here. So when you sum over all this, denominator is just when nx prime equal to nx, right? So only the two summation become one summation. Two sides of summation become one side of summation. And y and z, c and x, let me just give you some hint about this harmonic oscillator. Then, since the idea is same, then you can do yourself. So I'm going to quickly, just a few minutes, go to this harmonic. not spherical harmonic, just harmonic oscillator. Anisotropic, that's the N. Let's consider anisotropic, anisotropic. So the Hamiltonian, potential, okay, because only potential has this different, system has different, so that's omega x square plus half n, omega y square plus half of n, omega z square. So when we say anisotropic, because the frequency, they are not same along the three direction. So if this, and we definitely know that it can written or separate, right? Separate into three parts, x components part, y components and z components. Then the Hamiltonian is separable. So we have, we solve this eigenvalue problem. The wave function is product of three parts. Time dimensional equation. Also, we have solved each individual, each one is one dimension, right? Go to 1D harmonic oscillator. So we can directly use the result from the harmonic oscillator in 1D, since each direction is totally one dimension problem, right? So the solution, solution. Energy, again we have three quantum numbers. Since we know this harmonic oscillator is dependent on this quantum number, it's also quantized, right? So let's just give you the energy. Three quantum number. E and X and Y and Z, and they are same as like H bar omega X, NX plus half plus H bar omega Y, NY plus half, and H bar omega Z, and Z half. Here, what is NX, NY, and Z? In this case, quantum number from 0, right? We know because the zero's energy is this term, half. So that in this case, quantum number is from 0, when and 1 to all this integer number. Now the wave function is also the product of three parts. And each part we already discussed in the one dimension. We either use the analytic method or algebraic method. All the methods give us the function is like a Hermite polynomial, right? So now let's just give you final result is x, nx, y, and y, and z. And each one has its coefficient, so now I'm giving the coefficient here. Omega m3 and omega x, omega y, omega z, over pi q, h bar q, 1/4, then 1/square root, factor 2 nx plus ny plus nz, and then this nx factorial, ny factorial, nz factorial. Then multiply the Hermite polynomial for each component h and x, which is the variable is omega. m omega x over h bar x, and y part m omega y h bar y is a z component part squared m omega z over h bar z. Then the exponential term, which is the envelope, to control the convergence of this function when x r goes to infinite, right? That's remember this term. Minus m 2h omega x squared plus omega y squared plus omega z squared. Okay. I leave the discussion yourself, and also textbook has a discussion, so you can also refer textbook. So for example, this ground state. First, excited state, degeneracy, and then if is isotropic, right? Isotropic harmonic oscillation. Later, what that means, omega x equal to omega y equal to omega z. Then discuss ground state, degeneracy. For example, first excited state. Okay, so these three types of potential in the Cartesian coordinates we discussed and have some idea about this difference. And in general, the potential may not only this box or spherical harmonic or free, maybe the mixture of the, for example, along the x is harmonic oscillator, along y is like a box potential. Then you put together, that is the total potential for this system. So you need first to analyze if this potential is separable. If yes, then Hamiltonian is separable. But then you solve this, each individual, because potential different. So your solution different type. This one may be harmonic. This one may be the kind of infinite square wave. This one may be some others. Then you put all the energy together, all the wave function together. Then you can discuss, right? So just extend this. We do each individuals, then you can extend to any arbitrary combination of the potential. If they are separable, you follow the same scale. The only difference is you deal with each individual, be careful. They are not the same type of potential. All right, so this semester we covered almost the 5 chapters, but chapter 6 also begin with 2 sections. So that will go to our, chapter 3, section 6, right? And until here is our topics will be covered in this final exam. Can you deliver? My pen is dirty. This is take home final exam, and there's 3 questions or 3 problems cover the chapter. I think 4, 3, 4, 5 or something. And chapter 6. Let me see. Yeah. Chapter 5. We have 2. Number 2 and 3 are chapter 5, right? About this angular momentum or spin. First one is chapter 4. Then in class, it will another 3 problems will include this. One of the problems will include chapter 6. So I would like you to just go to the textbook. If you have time, just do one practice. See, yeah. That is, I think this is not difficult for you. I guess. From your homework, I think Actually it is not hard. So yeah, you can do right now. Of course, independent, no discussion, but open textbook, open notes, and open your.
I've heard that from many professors before,
Mm-hmm.
but for some reason, I want to believe you.
You won't believe me.
I do.
Thank you.
I've never heard the words obviously, easy, or as you can see from a professor where I didn't immediately follow with, what?
Okay.
But I want.
If you go, yeah. I think the number one, this is like a potential stack, right? We already you go to 1D, we have a potential stack, and depending on where the energy is higher or lower, you have either transmission or like a bounce back and the coefficient, something like that. Okay, you can go to look at the one. If you have any question, say I do not understand the question, let me know. Okay, or the first problem already gave you the wave function, right? So ask you just to calculate this, find the probability density in terms of A, B, C, and K1, K2. Probability density is the definition, right? Psi square. Yes, and then you're going to, but of course in the different region, right? Then this delta x is give you the, in this case, B, plot the probability density. That if you have the function, you can plot. Next textbook has also checked it. Something like this, right? This figure. So I think you know the function, you know the behavior, either sinusoidal or decay, so you can plot, right? So I think A and B is not difficult. C is that penetrate. Let me see. The energy is twice. If the potential energy equal to twice of kinetic energy, so that means energy is lower than potential, right? So you have cannot 100% go through. You have like here and trying to decay certain displays, and then ask you calculate that one. If a decay, the exponential term equal to that one, then how much delta x? When you have a delta x, you can estimate delta px, right? By this uncertainty principle.
It says in the parentheses for
Uh-huh.
1C,
Uh-huh.
the e to the power of -2 k2
Yeah.
delta x equals e to the -2.
Yes.
Where does that come from?
It's a give you condition. Suppose the delta x equal, that asks you to find the delta x. Find when, how much delta x is such that this exponential equal to e to the -2. That makes sense? Yeah.
So isn't that giving us the? Oh, okay, I see.
Yeah. That is that is give you condition if that equal how much delta x is. Okay. The second one, I do similar problem in the class for the spin along this I think xy or another one of plane, right? Here this is a yz plane, right? So you just go back to that the notes, and also there are examples in textbook. The orientation is slightly different. Either along the xy plane or yz plane or zx plane. So only different. Then once you have that idea, you can solve the eigenvalue problem, find eigenvalues, eigenstates, and then the others. All the question you can do. Number 3, chapter 5, right? I gave you the result. This L square and LZ, I think, and plus minus the result. But ask you to prove how to obtain this result, and you just try to find in the Cartesian, Lx, Ly, how to convert to the spherical coordinates. Then when you know the Lx, Ly in spherical coordinates, you can find the real plus minus, right? Yes. So I think that is not difficult. Okay. Any question if you have, stop to my office and I'm going to explain if you do not understand the question. All right. Good luck. And yeah, next Monday, right?
Yep.
One, right? I already reserved this room. At 1 p.m., bring your final, take it home, and then we are going to take the in-class final exam. Okay.
We come in at 10 for our lecture.
Tomorrow we have discussion. Classical mechanics.
Yeah.
Classical mechanics. What's the time frame?
We can do it right after the lecture tomorrow. 10 a.m.
10
For the
a.m.
plot, should we just sketch the general shape?
Yes, yes,
Dr. Yu.
yes.
So 10 a.m. tomorrow for classical?
Yes, 10 a.m., yes. I'm coming. I will be there.
Oh, y'all got your classical final tomorrow?
No.
Not
Oh.
that's
It's a lecture.
it's a kind of discussion and,
Okay,
yeah, like dissertation.
That's
gotcha.
good, that's good.
Yes, good, yeah.
It's not for 3
I
more
wish
days.
we had
Kyle.
that for StatMech.
But if you want to join, you can come here for the same day, I mean, same time after we discuss this.
And then ask questions
Question
about
about
StatMech?
content. No, no.
Oh.
Okay.
I have to put quantum mechanics on the back burner for a minute
Okay.
until after Wednesday.
Yes.
After Wednesday, yeah, I know
Yes.
you are busy, another due, right?
StatMech final on Wednesday.
It's in class,
Yes.
Yeah.
open book?
That one, yeah,
It is open book, but they're all like 5 to 7 hour long, so.
I know it's insane, but
Okay.
it's okay.
Good luck, I just appreciate it, good luck.
Thank you. Thank
And
you.
it's like 5 to 7 hours of feeling like you're the dumbest person on earth.
Because it's like,
So that is non-linear, I know it's already non-linear.
Yeah, we're doing non-equilibrium type stuff right now, so.
Okay.
He kind of gave the hint that the
I
test would
literally
probably
picked up
be
my camera
mostly
right before I
rate
left,
equations.
so I don't
and
know
the proper
like
blank
what I do with it. Because I picked up my
So you can
I
write
picked up my
correct
camera
equations
because I was charging the battery.
we'll at least
I
get
put the new
partial
battery
credit.
in, and I guess when I got to my car and
Like
I
you
opened it, I'm
said
like,
earlier, if we
what's
write
going
out
on?
100 pages, then we
I
get
had a moment where I
credit for
lost
that,
something
right?
Oh,
in front of
okay,
everyone
yes,
this
yeah.
weekend.
That's
Where
easy, right?
we were
100
talking about
pages.
like restarting the
You
movie,
something-
and I was like, here, I'll do it.
In the
Like
100 pages, right?
I picked
And
it
you
up,
can
and I was like,
find
where do we
what
want to
you're
go back to?
thinking.
And then like
I
in the
feel
discussion,
like if we
I
turned in
ADD'd
100
and wandered
pages
off a little
to
bit.
see, you just
It was like,
be
okay,
like,
we can just start. It's here.
Why'd you
Okay.
do all this?
Does anyone know where remote?
We might.
And they were like, how did you lose it in the conversation? I have no idea, and it took